state, right? So for an ideal gas, by using this equation of state, we can try to solve one question, one problem in the next slide. That is, let's try to solve this example. A student comes to school by a bicycle, which tires is filled with air at pressure 240 kilopascal and 27 degrees Celsius. Right here we have a pressure P and we have a temperature T. She travels 8 kilometers to reach a school, and the temperatures of the bicycle tires increases to 39 degrees Celsius. So T1 will be 27 degrees Celsius. After some times, T1 reaches to 39 degrees Celsius. Right. What is the change in pressure in the tire when students reaches school? Right. Can you be able to solve this question? Just simple questions. I already hinted the answer. Yes, you can use the equation of state for an ideal gas formula. Right. Here we have T1 240 kilopascal and T1 27 degrees Celsius. So after some times 27 degrees Celsius T1 reaches to T2 39 degrees Celsius, then we can use the formula, right? So directly we can look at these solutions. We can take air molecules in the tires as an ideal gas, right? So inside the tire there will be air molecules that will be considered as an ideal gas. The number of molecules and the volume of the tire remain constant. So there is the volume will be constant and the number of molecules present in the tire inside the tire will be a constant. So the air molecules at 27 degrees Celsius satisfy the ideal gas equations, right? So PV is equal to NKT. So at the state 1, we can have the equation P1 equal to NKT1. So N and K is a constant, so we can give the constant as constant. And in 39 degrees Celsius, we can have the formulas P2 equal to NKT2. Here N and K are constant, so we are keeping the constant as such, right? Then already we are getting the answer, but we know, so from this equation here in this tire V1 is constant, right? So volume of the tire is constant, so we have volume 1 and volume 2 of states. In state 1 volume also constant, state 1 volume equal to state 2 volume, right? So we can have the formula P1V equal to NKT1 divided by P2V is equal to NKT2. So we can rewrite the formula. In this manner. So P1V divided by P2V equal to NKT1 divided by NKT2. Yes, we can cancel the constants values. Yes, we can cancel the constant values. Here V is constant, NK is constant, so we can cancel and we can have the formula P1 by P2 equal to T1 by T2. Right. So also we can rewrite this formula P1 by P2 is equal to T1 by T2 as P2 equal to. So we can bring P2 another side, then we can bring down the T1 in another side. So P2, we can have the P2 equal to P1 into T2 by T1, right? So this is the formula we need to derive. So we can find the pressure at state 2 by using this formula, right? So we can substitute the values already we have. So we know T2, we know T1, we have P1. So if you substitute the values in this equation, then we can find the value of P2. So you can find the values of P2. So the temperatures will be taken in Kelvins, right? So just 39 degrees Celsius and 27 degrees Celsius were converted into Kelvin. So each and every calculations you have to put the temperatures values in Kelvins alone. Try to keep in mind. Then we can enter the values of T2 and T1. So T2 values will be 312 Kelvin. Then T1 values will be 300 Kelvin. Then pressure in kilopascal. So just we have to put the pressure in pascals. So 240 into 10 to the power 3 pascal. So if you solve this, if you calculate these equations, you can get the value 249.6 kilopascal, right? So by these equations we can solve this kind of problems, right? So we have to know what is the equation of state and where it can be applied. So by to solve this problem, we can use the equation of state of an ideal gas. So with these introductions, we can move to the next portions. Already we discussed internal energy. So internal energy is the addition of kinetic energy and potential energy. Then you know what is quasi-static process. So quasi-static process is an head flow process. This is an example of a quasi-static process. So by adding a small changes in the system, we can have the quasi-static process. Sorry. Then already we discussed what is the all the types of systems available. So we have open, closed, and isotropic system. Then what is matters? Then how heat and work are important in this thermodynamics. Then what are the processes involved in thermodynamics? We will discuss these processes in detail in the coming slides. Then temperatures. Then pressure. These are the parameters. These are the functions of the states. These are the functions of the state, point functions. Pressure, temperatures, volumes will be functions of the each and every states. So we have discussed. And then what is the heat and work, and both together involved in the thermodynamics. Then what is the reversible process? Then what is work? Then state functions in thermodynamics. Then heat capacity, right? So if you want to know more about what is heat capacity, in the last class we discussed about what is heat capacity. So heat capacity is an amount of heat needed to raise an unit amount of substance by unit in temperatures. So this is a heat capacity. So we can have much more clear about what is heat capacity. So heat capacity and a specific heat capacity. We have two terms, heat capacity and a specific heat capacity. So heat capacity, take equal amount of water and oil at temperature 27 degrees Celsius. Right. So we can have water as well as oil at the same temperatures and heat both of them till they reaches the temperature 50 degrees Celsius. Right. So just imagine this scenario. We can have water as well as oil at 27 degrees Celsius. We want to reach this temperatures 27 degrees Celsius to 50 degrees Celsius. Right. Will they take the same time? Right. Let me see. Note down the time taken by the water and oil to reach the temperature 50 degrees Celsius. Right. Just if you see the time taken to reach the temperature 50 degrees Celsius, obviously these times are not same. Right. So we can see that water takes more times to reach 50 degrees Celsius. So the oil will take 50 degrees Celsius within less times, but the water will take more time. to reach 50 degrees Celsius, it implies that water requires more heat energy to raise its temperature than oil. So we can clearly note on the point. Water requires more heat energy to raise its temperature than oil. Now take twice the amount of water at 27 degrees Celsius and heat it up to 50 degrees Celsius. Note the time taken for this rise in temperatures. So again we are repeating the experiment by taking water 2 times compared with the oil. Then again we are noting the temperature. We are noting the time to the temperature reach 50 degrees Celsius. The time taken by water is now twice compared to the previous case. So say for example, if 5 minutes in the previous case, if we twice the amount of water, the time will be 10 minutes, right? So the time taken will be 10 minutes. So it will also twice. If you increase the volume by twice, you can also increase the time by twice. We can define heat capacity as the amount of heat energy required to raise the temperature of a given body from T to T plus delta T. So from initial temperature T to final temperature T plus delta T. So there will be an increase in temperature. So this is called a heat capacity. Just you have to understand this one. The heat capacity, the amount of heat energy required to raise the temperature, right? So this is the definition of heat capacity. So we can have the formula: heat capacity S is equal to delta Q by delta T. So heat energy, Q is heat energy and temperature is T. So delta T is a change in temperature, change in heat energy, and then delta T is a change in temperature. So we can have heat capacity formula as S is equal to delta Q by delta T. Then this is the heat capacity. Then also we can have specific heat capacity. So each and every properties, each and every functions will have specific functions. So we if volume is there, we can have specific volume. If density is there, we can have a specific density. If any other functions is there, we can also have specific functions. So like that we can have specific heat capacity. So heat capacity, we know what is specific heat capacity. A specific heat capacity of a substance is defined as the amount of heat energy required to raise the temperatures of 1 kg of substance. But the point, 1 kg of substance by 1 Kelvin or 1 degree Celsius is called a specific heat capacity, right? We know what is heat capacity. So if the heat capacity of 1 kg of substance to raise 1 Kelvin is measured, that is called a specific heat capacity. Just you can note on the definition of specific heat capacity. The specific heat capacity of a substance is defined as the amount of heat energy required to raise the temperature of 1 kg of a substance by 1 Kelvin, right? So if a specific if a term specific is implemented, so we have to take the measured quantities. So here the substance will be 1 kg and we are increasing the temperature by 1 Kelvin. So we can have this specific heat capacity. So these are the definitions. Then this is the formula. So we can have delta. We can also rewrite the equation. So rewrite the equation. So their heat capacity is capital S and specific heat capacity is small s. So from this equation, so from this heat capacity, we can derive the specific heat capacity equation. Small s is equal to 1 by m delta Q by delta T. That is the mass dependent. So we have 1 kg of mass here. So we can have the specific heat capacity by calculating by increasing the 1 Kelvin temperature. We can just remember this equation for specific heat capacity. Then So in these equations, we have S is in specific heat capacity, then M is in mass of the substance, then you know delta Q, amount of heat energy, then delta T, energy, temperature. The SI unit of specific heat capacity is joule per kilogram Kelvin. Then heat capacity and specific heat capacity are always positive quantities, right? Right. These parameters will be a positive one. Then the unit will be joule per kilogram Kelvin. Right. So when we study properties of gases, it's more practical to use molar specific heat capacity. So the next term introduced, molar specific heat capacity, the same. There is mass is considered. There is molarity. Molar is considered. Molecular quantity is considered. So it's more practical to use molar specific heat capacity. Molar specific heat capacity is defined as heat energy required. Heat energy required to increase the temperature of the 1 mole of substance. There 1 kg of substance, here 1 mole of substance. The definition will be same, but you have to note the point. So if you want to know what is molar specific heat capacity, so we have to introduce the substance 1 mole by increasing 1 Kelvin, right? So it can be written as the following equation. The symbol will be C, right? Here molar specific heat capacity, capital C, equal to 1 by mu, the number of molecules, and delta Q by delta T. The same formula, but we can rewrite as we want. So here C is the molar specific capacity of substance, and mu is the mole of number of moles in the substance. Then we know what is delta Q and what is delta T. Then the SI unit will be also same, right? There joule per kg Kelvin. Here we have joule per mole Kelvin. It's also a positive quantity. So each and every properties where we discussed is positive quantities, right? So like in the previous case, we have molar specific heat capacity. Also we have specific molar heat capacity. So what is specific heat capacity of a gas? So also we have another definition of specific heat capacities of a gas. So specific heat capacity of a given system plays a very important role in determining the structure and molecular nature of the system. So we are discussing about the system. So we want to know what is specific heat capacity. Unlike solids and liquids, gases have two specific heats. One is a specific heat capacity as constant pressure and specific heat capacity as constant volume. So we have the specific heat capacity for all the states like the solids, liquids, and gases. But gases have two specific heats. One is the specific heat capacity at constant pressure and the specific heat capacity as constant volume. That is SB, SP, and SV. Then the specific heat capacity, we can define what is specific heat capacity at constant pressure. So the amount of heat energy required to raise the temperature. The definition will be the same, but just note on the changes in the definitions. The amount of heat energy is required to raise the temperature of 1 kg of substance by 1 Kelvin or by 1 degree Celsius by keeping the pressure constant. Right? If you increasing the temperature 1 Kelvin for an 1 kg substance with the pressure constant, that process is called as a specific heat capacity at constant pressure. So when the heat energy is supplied to the gas, it expands to keep the pressure constant as shown in figure. So we can have a much more clear about the specific heat capacity at constant pressure by seeing this figure. So just consider this piston cylinder arrangement. This cylinder is insulated. This cylinder is insulated, Then the piston, yes, we can move the pistons up and down. Then the bottom side will be a conductor, so we can add the heat by heating this piston cylinder arrangement. So how can we keep the pressure constant? In this process, a part of the heat energy, right? Just imagine this figure. Just we are adding the heat by heating this piston cylinder arrangement. Right. So assume this figure. So we are adding the heat into the system. So there is no chances to escape the heat. Right. There is no chances to escape the heat inside the piston because we provided insulators. So insulators. So what can happen? So in this process, a part of heat energy used for doing work, expansion. So the expansion will happen, and the remaining part is used to increase the internal energy of the gas. So the expansion also will happen, and then there will be an increase in internal energy. So this we can have much more clarification in the next stage. So what is specific heat capacity at constant volume? So here so in the previous case we can change the volume of the cylinder, but in this case we can't change the volume of the cylinder. So the volume of the cylinder is fixed by the pin provided here. So also we are provided an insulator. So we are adding heat by using this heating mandrel. So what will happen if you add heat to the system? So the volume will be changed. The volume will be same, and there will be changes in the properties. So we can have specific heat capacity at constant volume. The amount of heat energy required to raise the temperature of 1 kg of substance by 1 Kelvin by keeping the volume constant. Right. So in this way we can have the volume constant. So this process is called specific heat capacity at constant volume, SV. So in the volume is kept constant. If the volume is kept constant, then a supplied heat is used to increase only the internal energy. Right. So there is no work. There is no work. No work is done by the gas as shown in figure. Right. So we can have only the change in internal energy, but we can't expect the work from this system. Right. So it implies that to increase the temperature of the gas at constant volume requires less heat than increase the temperature of the gas at constant pressure. Right. So in the previous case, the work also will be there. There will be an increase in internal energy also will be there. But in this case, only change in internal energy is happening. So we need less heat energy compared with the previous case here. So we can compare these two processes. What is specific heat capacity at constant pressure and specific heat capacity at a constant volume. So specific heat capacity at constant volume will increase the temperature of a gas at constant volume. It was less heat than increasing the temperature of a gas at constant pressure. So we can differentiate these two processes. In other words, SV is always greater than SV. So we can have SV, specific heat capacity as a constant pressure process, is greater than SV. right? Specific heat capacity at constant volume process. Then molar specific heat capacity. Sometimes it is useful to calculate the molar heat capacities Cp and Cv. Same, there is 1 kg of substance, here is 1 mole of substance, right? The amount of heat required to raise the temperature of 1 mole of substance by 1 Kelvin at constant volume is called the molar specific heat capacity at constant volume Cv. If the pressure is kept constant, it is called a molar specific heat capacity at constant pressure Cp. Right. So the definition will be same, but there will be some changes. Right. Just try to note down the changes. So we can have the definition about specific molar specific heat capacity at constant pressure Cv, sorry, constant volume Cv, and molar specific heat capacity at constant pressure Cp. So if Q is the heat supplied to the mole of a gas at constant volume, and if the temperature changes by an amount dt, that is small changes in temperature, so we have the equation Q is equal to mu Cv delta T. This is the equation about the molar specific capacity. Here Q is the heat energy, and mu is and molar number of moles. Then Cv is the specific heat capacity, molar specific heat capacity at constant volume, then delta T, change in temperature. By applying the first law of thermodynamics, we will look at what is first law of thermodynamics in the next class. So by applying the first law of thermodynamics, for this constant volume process, the work will be 0. So for constant volume process, work is 0. And there is a change, there is no change in volume. So we can substitute in this first law of thermodynamics. What is first law of thermodynamics is delta U is equal to Q minus W. So we will look at that later. So just if you substitute this portion, 0 is a work. Then delta U, there is a change in internal energy, and there will be a Q, heat energy. So Q is equal to delta U minus W is the first law of thermodynamics here. So if you substitute the values for the constant volume process, we can have the equation Q is equal to delta U. Right. Then by comparing the equations of above, we can have delta U is equal to mu Cv delta T, and we can reorder these equations. Delta U is equal to mu Cv delta T as Cv is equal to 1 by mu delta U by delta T. So we can have Cv alone, and we can bring down the other values to the other side equal. Then we can have the equation Cv is equal to delta U by mu delta T. Right. If the limit dt goes to 0, we can write the equations Cv is equal to 1 by mu du by dt. So here there is no change. So we can also rewrite the equation Cv is equal to 1 by mu du by dt. So we can rewrite delta U to du and delta T to dt. So since the temperatures and the internal energy are state variables, the above relation holds true for any process. So values the Cv and T is the variables of the internal energy. So the equation will happen in all these stages. Right. Then we can have a Mayer's relations. What is Mayer's relations? So consider mu mole of an ideal gas in a container with volume V, pressure P, and temperature T. Right. So when the gas is heated at constant volume, the temperature increases by heating. Ganesh Kumar, just unmute your S. Right. right? So we can continue. So here, when the gas is heated at constant volume, the temperature is increased by dt. So as no work is done by the gas, the heat that flows into the system will increase the only internal energy. Let the change in internal energy be du, and if C is the molar specific heat capacity at constant volume, from equation from the above equation, so we can have the equation delta U equal du is equal to mu Cv dt. Suppose the gas is heated at constant pressure, so the temperature increases by dt. If Q is the heat supplied in this process, and dV is the change in volume of the gas. So this is constant volume process, and this is a constant pressure process. Then we can have the equations Q is equal to mu Cp. Q is equal to mu Cp dt. So if W is work done by the gas in this process, so during constant volume, constant pressure process, we can have the work done. W is equal to PV. So we can have the work done. W is equal to pressure into change in velocity. Pressure and into change in velocity. But from the first law of thermodynamics, we can write, we know what is first law of thermodynamics. Q is equal to du plus W for the system. So we can substitute the values of W and Q in this first law of thermodynamics, and we can have mu Cp dt is equal to mu Cv dt plus bdv. So we can substitute. So Q for Q, we can substitute mu Cp dt. For du, we can substitute the value from 8.21, that is mu Cv dt, and we know W is equal to P dV. Then for mole of ideal gas, the equation of state is given by PV is equal to mu RT, right? So also we can have the ideal gas equation as PV is equal to mu RT. Here mu is a number of moles, and R is an universal gas constant, right? So we can change this equation by definition, differentiate these equations. So we can have PV, and if you differentiate PV, we can have PdV plus VdP. So this is the equation from mathematics. This you know. To differentiate the two variables, we can have this equation: PdV plus VdP equal to mu R dt. Just we are introducing the differentiation in both ends. So then we can have this equation PdV plus VdP equal to mu R dt. Since the pressure is constant, so in this constant pressure process, you know, the change in pressure is 0. So we can cancel the this value B dP as 0. Then we can have the remaining parts Cp dt equal to Cv dt plus R dt. We here we cancel the mu's, just substitute the values in this. So we can have we can substitute the value of PdV here. So here we can get PdV equal to mu R dt. Then if you substitute this PdV value in the equation 8.25, then we can have the mu on the all values. Then we can cancel the constant value. So mu and dt, yes, mu and dt will be same for all the values. So we can cancel that value, cancel the constant values. Then we can have the values only Cp equal to Cv plus R. Cp is equal to Cv plus R, or we can rewrite the equation Cp minus Cv is equal to R. Right. So this is the Mayer relation. This is called a Mayer relation. So we just keep in mind Cp minus Cv is equal to R. So here Cp will be more compared with the Cv. Then only we can get Cp minus Cv. That is R is universal gas constant. So it implies that the molar specific capacity of an ideal gas at constant pressure is greater than the molar specific capacity at constant volume. So from this relation, we can get that point. The relation shows that a specific heat at constant pressure is always greater than the specific heat at constant volume, right? We know. So Cp is greater, Sp is greater than Sv. Then we discussed the zero law of thermodynamics, and we can look at what is the zero law of thermodynamics. When a body A is in thermal equilibrium with body B and also separately with body C, then both then B and C will be in thermal equilibrium with each other. So this is the zeroth law of thermodynamics. I am repeating, when a body A is in thermal equilibrium with body B, right? So A is there, then B is there. So these two are in thermal equilibrium and separately with body C. So we have another body C, and this was in contact with the body A. Then B and C. So this B and this C will be in thermal equilibrium with each other, right? Because but B and C is not in contact. So B and C is not in contact. But this B and C will be in thermal equilibrium because of the zeroth law of thermodynamics. We can move to the next law. First law of thermodynamics. So first law of thermodynamics is a statement of the law of conservation of energy. So we can have another law, conservation of energy. It will be same as the first law of thermodynamics. So in the Newton's mechanics, conservation of energy involves kinetics and potential energy of bulk objects. So in mechanics, we can have the kinetic energy and potential energy for bulk energies, for bulk objects to consider the energy equation. But the first law of thermodynamics includes heat also. So this first law of thermodynamics is added heat with the kinetic energy and potential energies. So we can define this law. The law states that change in internal energy. So this is the first law of thermodynamics. Change in internal energy delta U of the system is equal to heat supplied to the system minus work done by the system. Just to note on the key points: heat supplied. Also, we can have heat release, and the key point work done by the system. Also, we can have work done on the system. So there will be a changes. Just keep in mind. So from this definition, the change in internal energy of the systems is equal to heat supplied to the system minus heat minus work done by the system. Okay, supplied to the system minus work done by the system and the surrounding. So mathematically, so also surrounding are on the surrounding, right? So mathematically, we can write as delta U is equal to Q minus W. So delta U, change in internal energy, equal to Q minus W. Here minus happened because work done by the system. So also we can rewrite the equation delta E is equal to plus or minus Q plus or minus W. So here we can have plus or minus Q values. So if heat supplied to the system, we can have Q as plus positive value. If the heat is rejected from the system, we can have Q as minus W. Also, we can have plus or minus W. So if work done on the systems, the W will be positive. The W value will be negative. So here in definition we can have we have put done by the system, so we can write the equation of first law of thermodynamics as delta U is equal to Q minus W. So also there will be equation delta U is equal to Q plus W. Also we can rewrite the equations minus Q plus W and minus Q minus W. So we can have a lot of equations of first law of thermodynamics based on the parameters involved in the systems. Right. So that was discussed in the following table. If heat energy flow into the system, what will happen? The internal energy will increase. Right. Just you can assume, and just you can imagine. Right. If we add the heat to the system, definitely there will be a change in increase in internal energy. If heat flows out of the system, the internal energy will decrease. That's why we have a positive value. So for heat flow into the system, heat supplied to the system, if heat rejected from the system, if heat flows out of the system, we can have a minus value of Q, and the internal energy will decrease. Then work done on the system. Work done on the system. So we are doing work on the system. The internal energy increase. So why we are doing system? Why we are doing work on the system? To increase the internal energy of the system. Right. So if work done by the system, the internal energy will decrease. So just try to compare these values. So if heat flows into the system, the internal energy increase, and value for Q will be plus. If heat flow out of the system, the internal energy will decrease, and the value of Q will be minus. If work done on the system, the internal energy increase, and the W will be plus, and the work done by the system, the internal energy decrease, so W value will be minus. Just try to compare these points. Then based on the previous tables, the sign conversion is introduced to use first law of thermodynamics appropriately in the following figure. Right. So the system, if the system gains heat, so heat Q is positive. If system gains heat, Q is positive. Right. As we discussed in the early. So system gains heat, Q is positive. If the system is lost heat, Q is negative. If work done on the system, W is negative. Yes, keep the point. Work done on the system. Yes, we are doing the work done. So W will be negative. So we are doing what? Then work done by the system, so W is positive. So we can consider these figures. The sign conversion for heat and work is can be imagined by these following figures. Even though we often explain first law of thermodynamics using gases, the first law of law is universal and applies to liquids and solids also. So we can use this first law of thermodynamics for liquids and solids also. So in general, we will use the first law for gases. So the figure shows you the sign conversions of heat and work. So in the first figure, so heat is supplied. Q is positive, and we are raising the piston above. So here the work is done by the system. Right. Here work is done by the system. So we can have the work W value positive and Q value also positive. So we are supplying the system. So Q is positive, W is positive in the first figure. Then in the second figure, yes, we are doing the work by compressing the piston. Yes, we are doing the work by compressing the piston. So W value will be decrease. W is decreasing. Then also we are providing the heat adding to the system. So Q value will be positive. And in the third figure, so we are not heating the system here. Just there will be a conduction. So just we are doing work also to the system. So W will be decreasing. Also QRE also decreasing. By doing work, the temperature inside the system will uh, uh, try to go out. Now in the figure 4, we are not doing the work, but the system itself doing work. So Q also decreasing, W also. W is increasing because we are done by the system. Here the done by the system is happening, so W is positive, right? So just go through this table and figure, then we can have the idea about the system heat added to the system and heat rejected to the system by the system, work done on the system and work done by the system. In Q1 W. So we can use the first law of thermodynamics to solve this example, to solve this problem. Just read the problem. A person does 30 kilojoule work on 2 kg of water by stirring using paddle wheel. By stirring, around 5 kg 5 kilocalories of heat is released from water through its container to the surface and surroundings by thermal conduction and radiation. What is the change in internal energy of the system? So just read the questions once again. So we can have the functions and we can have the what to find. So here 30 kilojoule work on 2 kg of water by stirring using paddle wheel. So just assume this example. So we are stirring of water of 2 kg and we are doing work by 30 kilojoule. By stirring, around 5 kilocalories of heat is released. So the Q is released, right? Right. There is conduction and radiation. What is the change in internal energy? So what do you want to find? So change in internal energy delta U. How can we find the solution? Work done on the system. So here work done on the system. So W equal to minus 30 kilojoule. So we can convert this kilojoule into joule. So we can have W is equal to minus 30,000 joules. Then heat flowing out of the system, right? So Q is minus 5 kilocalories. So we can convert these kilocalories into joules by multiplying with the constant value. So 5 into 484 joules. So we can have minus 2920 joules. So we have what W and we have Q, and the sign conversion is very important here, right? Just put them on the system, W minus, put them on the system. So W minus heat flowing out of the system, Q minus, right? So using first law of thermodynamics, we know the equation. So Q delta U is equal to Q minus W. So we know we can substitute the values. So minus 20, 920 minus of minus 30,000. Yes. Then we can calculate delta U as 9080 joule. Why the sign conversion changed into plus? Here the heat lost is less than the work done on the system. So the change in internal energy is positive, right? So like that we can calculate internal energy, change in internal energy of a system, right? Here water is a system. So we are doing a work by stirring and the values are given, and the heat released value is also given. So if you want to find the change in the system, we can calculate therma. Right, fine. So this is the application of first law of thermodynamics. So we can use the first law of thermodynamics to solve these kind of problems. So just to go through this problem, then move to the next slide. Next example. Yes, jogging every day is a good for health. Assume that when you jog a week of a work of 500 kilojoule is done and 230 kilojoule of heat is given off, right? What is the change in internal energy of your body? So here is another example of first law of thermodynamics. We can find the change in internal energy of the of our body, the system, by using the first law of thermodynamics. So we have to note down what is the value for W and what is the value for Q. So here work done by the system, right? The body is doing work, so W value will be positive 500 kilojoule, and heat released from the system, so the Q value will be minus. So if you apply this value to the first law of thermodynamics, then we can have delta U is equal to Q plus or minus W. So we can have minus 230 kilojoule minus 500 kilojoule as minus 730 kilojoule. So this is the change in internal energy. So there is we are losing the internal energy. So by jogging, why we are jogging? To lose our fats, right? So because the decrease in internal energy of our body, we can burn our calories. So so we can use the first law of thermodynamics to solve these equations, to solve these problems, right? Right, move to the next step. Work done in volume changes. To consider a gas contained in a cylinder fitted with the move piston, right? So consider the piston cylinder arrangement. So we can move the piston up and down. Suppose the gas is expanded quasi-statically by pushing the piston by a small distance dx as shown in figure. So here this is the initial state. So here V1, here P1, and we are changing. System is doing work by changing dx distance. So in this, the system is moving up. The change in different distances dx. Since the expansion occurs quasi-statically, the pressure, temperature, and internal energy have unique value at every instant. So dx is not a single process. So infinite process will raise this piston to dx distance, right? So quasi-static, you know what is the value of what is the meaning of quasi-static? So this dx will attain by infinite process. So this will go this. So infinite process joined together will give you to raise the piston of up to dx, right? The small work done by the gas on the piston, we can write, from the work done equations. Work done W is equal to F force into displacement. From the physics, work is equal to force into displacement. So from that equations, we can write this dW is equal to F dx. Right, small work happen, and by changing small distance, right, small displacement. So we can have the equation dW is equal to F dx. So here dW is small work then dx is a small distance traveled. The force exerted by the gas of a piston F is equal to pressure into area. We know the equation force. Force is equal to pressure into cross-sectional area of the cylinder. So we can have F is equal to P into A. Then we can substitute this F is equal to P into A in the above equation. Okay, A is the area of the piston, right? So P is the pressure exerted by the gas on the piston. Then we can derive the equation as dW is equal to PA dx. So we are substituting the value of F as PA. And we can have dW is equal to PA dx. But so we know A into dx, the cross-sectional area into the change in distance is increased in volume, right? So increased in volume, that can be written as dV, change in volume, right? Change in volume can be written as dV. So we can write A into dx as dV, that is the change in volume during this expansion process. So the small work done by the gas during the expansion is given by, we can derive the equation dW is equal to P dV. So we are changing A dx as dV. Note here that is positive since volume is increased. Okay, so because volume is increasing, we can have the value positive, value plus. In general, the work done by the gas is increasing the volume from V initial to V final, right? So V initial in the first state, here V final in the second state. So we can have the values V initial to V final, and we can integrate this one. So if you integrate both the side, you can have dW. If you integrate dW, we can have W. If you integrate dV, we can have the values integration of V initial, V final, V dV. Vi in the sense V initial, Vf in the sense V final. Right. So we can derive the equation W is equal to derivation of Vi, Vf, Pdv. Suppose if the work done on the system V initial greater than V final, right? This is work done on the system. So then W is negative. So you know the W value here is positive. If we are work done by the system. If work done on the system means we can have W value as negative. Note here the pressure inside the internal pressure inside the integral in equation, it implies that while system is doing work, the pressure need not be constant, right? So here the pressure need not be constant, right? To evaluate the integration, wait a minute. Right, from this equation we can know the work done is a function of pressure and volume. Right, function of pressure and the volume of the system. So we can have the work done, and we will discuss what is the PV diagram. So the graph between the pressure and volume of the system, and the area under that curve will give you the work done. Keep in mind the work done can also be calculated by calculating the area under the curve. So we can draw the PV diagram. If you calculate the area under the curve, we can have the work done W. That is area is equal to area minus integration of PD. Area is equal to integration of PD. So we can have this area. There in the shaded area will give you the work done. That is integration of PdV value from initial to V1, V2, Vf. Both the values. So by using the formula, also will give you the calculation of the area. Right. So let me try to solve this problem. So this problem, we can stop the today class. Just try to solve this problem. A gas expands from 1 meter cube to 2 meter cube at constant atmospheric pressure. Calculate the work done by the gas. Represent the work done in PV diagram. Right? Can you able to solve this problem? Just try to solve the problem. Let's read the problem once again. Yes, a gas expands from 1 meter cube to 2 meter cube in volume at constant atmospheric pressure. Here P is constant, and we are changing the volume. We are increasing the volume. So calculate the work done by the gas. How can we calculate the work done W? The second question is represent the work done in PV diagram. So we can draw the PV diagram for this process. Right. At least a solution. The pressure here is atmospheric pressure, that is 1 atmosphere, 1 atm, that is 101 kilopascal, and V final is 2 meter cube, V initial is 1 meter cube, right? Then we can have the equation W is equal to integration of VI, VF, P dV. Here P is constant, so we can take the P outside. So we can have the equation P, integration of VI, VF, dV. So we can substitute, we know the value of VI and VF. Then since P is constant, we taken out the integral. So we can relate the equation W is equal to P, VF minus VA. We can substitute the values, the values of P and VF minus VI. Then we can have 101 kilojoule. Right. So the answer of first question A, the work done by the gas is 101 kilojoule here. Then move to the next second question. Represent the work done in PV diagram. Since the pressure is kept constant, PV diagram is straight line as shown in figure. So we can able to imagine the PV diagram. Pressure P in the x-axis. Here P is constant, so there will be a straight line horizontally in the PV diagram. So this is the PV diagram of this process. So here P and here V. So pressure 101 kilopascal is keeping constant, and from 1 meter cube volume in the x-axis increasing from 1 meter cube to 2 meter cube. Just we are increasing the volume. The area is equal to the area under the curve, equal to the work done by the gas. So we can compare these two values. So if we calculate the area, so we can get area under the curve. We can get a rectangle. So the value of the horizontal line will be 1, and the area of the vertical line will be 101 kilopascal. If we want to find the area of this rectangle, just we can multiply the length and the breadth. So we can have 1 into 101 kilojoule. So we can have 101 kilojoule work. So we can have this equal values in both the cases. Note the arrow mark. So in the PV diagram, here the process path. This is the initial state 1, and this is the final state 2, and this is the path. This is the path. This line, the red line is the path. So this part is traveling in this direction, so we are increasing the volume in this direction. Suppose the work done here, work done by the system, right? Suppose work done on the system, the volume will decrease, the arrow will be opposite direction. Just keep this point while drawing this DB diagram. So why we put the arrow direction in this direction? Because work done by the system. So if the arrowhead is in this direction, work done on the system will be there, right? So this is the equation. This is the application of the formula of W. So by this way, we can calculate the work done of a system, of a process. Right. So next classes we can discuss in details about thermodynamic processes. Just in brief, we know what is the thermodynamic process. Then in the upcoming classes, we will discuss the thermodynamic processes in detail. Right. So from this, we can stop the today class. If you have any queries, you can ask now, or you can hang up your Teams. Thank you. Have a good day. If you have any queries, you can wait and you can ask.
Thank you, sir.